We can now look at how optimization actually implemented in K-mine. Our approach starts with a simple idea. In underground mining, the key unit isn't a single block or even a group of blocks, but a stope. A stope already carries orientation, workable dimensions, economic meaning, and alignment with the chosen mining method. So instead of beginning with whichever algorithm happens to run fastest, we start with forming mining clusters that can genuinely be extracted under the site's geological and technical conditions. So the first step is building a geometric framework for the future Stope. The block model is grouped into clusters according to the ore body's strikes and dip, and only within the angular limits allowed by the mining method. This matters because underground methods are highly orientation sensitive. For example, when optimizing a vein deposit for mechanized cut and fill, we aim for narrow vein parallel stopes with minimal deviation. Otherwise, both planned and unplanned dilution increase. For sublevel stoping in a massive body, the stope can be larger and the tolerances on orientation are wider. And at the same time, the minimum and maximum cluster sizes are set. Small for narrow veins to capture local swelling, fixed to room dimensions for stratiform bodies, so room and pillar integration requires no change in discretization. So once the spatial structure is defined, optimization can now begin. In K-mine, the objective can be based either on quality or grade or on economics. A grade-driven mode works well for highly variable vein deposits where secure metal content is the priority. The economic mode is often preferred for more homogeneous massive bodies. For example, clusters are evaluated against cutoff, prices, and cost, and only those that provide a positive economic contribution remain in the stope. This avoids carrying marginal volumes that would later need to be trimmed manually. After choosing the objective, constraints are applied to the clusters in sequence. This is the heart of the process. So we start with geometric constraints. The stope must fit in the allowed height range, stay within the maximum width, and avoid shapes that create impractical tapers or bottlenecks. For gently dipping stratiform deposits laid out as room and pillar, spacing, room width, and height are dictated by the method, so the optimizer constructs stopes that follow those exact dimensions. For a stock work body under sublevel stoping with backfill, constraints reflect the allowable level height and room length, so the resulting stope is ready for design without later reshaping. So next come geotechnical constraints. Removing weak zones, limiting spans, enforcing sidewall stability, and if there is a section along deep with unfavorable fracturing, that section is simply marked as inadmissible and excluded even if grade is excellent. So this is crucial in faulted underground gold mines where rock quality can change dramatically within a few meters. Economic constraints are applied only after a cluster passes both geometric and geotechnical checks. Here, the system evaluates whether adding or removing a cluster helps or harms the economics, and in veins, this often focuses on dilution control. If an adjacent block brings too little metal but adds too much waste, it's left out. In massive bodies, slight reduction in average grade may be acceptable if they allow for cleaner, more productive mining shape. In all cases, the decision follows the configured rules that combine geometry, method, and economics. Refining the stope comes next. K-mine can adjust sidewalls, modify the stope's incidence relative to the ore body, and tighten adherence to the valuable zone. The method context matters. So for narrow gold veins, adjustments keep mining width minimal and avoid pulling barren rock. For sublevel stoping in massive bodies, a refinement smooths edges and remove block model artifacts, leading to more stable drilling and blasting and backfilling. The output is a set of stopes already shaped for immediate use in design. Another key feature is the ability to restrict optimization domain. Not every geometrical stope is practical at a given stage of development. Some areas may be inaccessible from current levels, located within the influence zone of active stopes, or positioned under protective pillars. In K-mine, the engineer defines the working volume, the portion of the model where extraction is currently allowed. If optimizing a room and pillar section between two ventilation drifts, there is no point in generating stopes outside of this window. Similarly, for sublevel stoping above a haulage level, the system can be instructed not to form stopes below a given elevation. So this keeps results aligned with the real mine constraints. Throughout the process, the optimizer remains aware of the intended mining method. When tuned for narrow vein mining, it uses small cluster and tight angular limits and stricter dilution control. For stratiform bodies and Rubin pillar layouts, it aligns stopes with grid-based mined discretization and preserves support pillars. For sublevel stoping in massive ore bodies, it emphasizes permissible heights and refined shapes to reduce backfill volume and simplify drilling and blasting. And all of this is handled during optimization, not after. So the stopes that move forward are workable, economically justified, and correctly oriented with respect to the ore body.